Alright guys, last thing to review for this test is Lewis dot structures. Now, I'm not going to go super in-depth because it's not really the point of emphasis for this test. The reason I included it, it was just kind of to give you a visual to help you understand what we were doing with the nomenclature. So I'm going to go over it a little bit, just the important stuff that you need to know. So basically, to draw a Lewis dot structure, all you do is draw the atomic symbol. So if we're going to do carbon, just a carbon atom, C, and then you draw in the valence electrons. So carbon, being in group 4, will have 4 valence electrons. So we do 1, 2, 3, 4. Okay, it's important to draw it like this and not like this and not like, you know, all over the place randomly. You want to do it like this. Okay? You just draw one at a time on each side, and then you're good. Now, if you had something like chlorine, Cl, chlorine's got 7 valence electrons. So we're going to do just like we did for carbon. 1, 2, 3, 4. Now we still have 3 more to put in, so we just kind of wrap back around. 1, 2, 3. So there's the Lewis dot structure for chlorine. Pretty easy. Okay? For an atom, all you really do is draw in the number of valence electrons. Now, where Lewis dot structures really come in handy is when you're drawing them for compounds. So if you have an ionic compound, let's say we have NaCl. We'll go with a simple one again. So Na and Cl. Sodium has 1 valence electron being in group 1, and chlorine we just drew, and it's got 7. So this is where I think Lewis dot structures can be really helpful because they show you what actually happens in a chemical reaction. So sodium and chlorine are going to form an ionic bond, right? Sodium, this one right here, its goal is to get to 0 or 8 valence electrons to be stable. Since it's only got 1, 0 is easier. So what it's going to do, it is going to give up its valence electron, and chlorine will happily take it because now it has 8. So what we've done, we formed a chemical bond here between sodium and chlorine. All right, sodium just formed a positive ion, and chlorine made a negative ion. The way you write this answer, if I ask you to write the Lewis dot structure for sodium chlorine, brackets, positive ion, brackets, negative charge. Okay? Here's your Lewis dot structure. Okay? So, what if we had aluminum oxide? This is always a fun one. So, we know right off the bat we have Al and we have O. Don't know how many, but we can figure that out. So we can use the crisscross method like we've been doing, but I'm going to show you right now why it works the way it does. So aluminum, group 3 has 3 valence electrons. Oxygen, group 6, will have 6 valence electrons. All right. So this is going to be an ionic bond. Aluminum is a metal, oxygen is a nonmetal. So aluminum is going to give away its electrons to try to get to 0. So it's going to give 1 over here. Oxygen will take it, and it's going to give away another one. Okay. Now oxygen has 8. It's happy. It does not want any more for aluminum, so it's not going to take that last electron. So what that means is we're going to need more oxygen to bond with. Okay, now this oxygen will take this electron. I dropped it. Okay, so now aluminum's happy, oxygen's happy, but this last oxygen's not. So we'll draw in another aluminum. And we're going to keep going until everything is stable. So it's going to give this one away. So now this oxygen's stable, but the aluminum that we just added is not. So we put in another oxygen. This does end, I promise. Okay? Now remember, this is for an ionic bond. And an ionic bond is when you transfer electrons. So aluminum gives one away here, and one away here. Now we finally got it. All three oxygen atoms have 8 valence electrons, so they're stable. Both aluminum atoms have none, they are stable. So for the Lewis dot structure, which it normally applies to covalent, but I wanted to show you how it works for ionic. Brackets, 3 plus, brackets, 2 minus. Now the only thing you have to add here is a subscript, since there are 2 aluminum atoms and 3 oxygen atoms. Okay, so this would be your answer. If I said give me the Lewis dot structure for aluminum oxide, that would be your answer. All right, now moving on from ionic, because I do want to get to covalent because that's where it's really important. So covalent compounds. Let's say we had carbon, that's a T, tetrachloride. Okay, we know from covalent nomenclature that this is going to be CCl4. So we can go ahead and draw that in. C, doesn't really matter where you put them right now. I'm going to put them here because this will make it look nicer in the end. So CCl4, there we go. So you first step, draw in these valence electrons. Okay. Doesn't really matter which side you start on. Okay. And these are terrible electrons, all right. Okay, so we've drawn in our valence shells. Now, since this is a covalent compound, they're not going to transfer electrons like we've been doing. They're going to share. Covalent means sharing. So the way to indicate this is you're going to circle bonding pairs, and I'll show you what I mean in a minute. So if you look up at this top chlorine atom, it's got 7 valence electrons. Only wants 8. So what it's going to do, it's going to form a bond right there. Okay? Chlorine is going to share one of its electrons with carbon, and in exchange, carbon's going to share one of its electrons with chlorine. Okay? When atoms share, it's always a 1-to-1 type deal. Carbon's not going to share unless chlorine shares too, so they're both going to share. So now if you count, this top chlorine has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. Okay, so he's stable. So let's look at the next chlorine. We can do the same thing. You count them up, and you're going to get 8 valence electrons again, so we're good. So you can probably guess what else is going to happen now. This bond is going to happen for all 4 chlorines. And to check your work, all you got to do is count the valence electrons. If they don't have 8, they're not done bonding, or you've done a bond wrong. If they do have 8, then they're good. So all 4 chlorines are good. Let's count carbon. 1, 2, 3, 4, 5, 6, 7, 8. Carbon also has 8 valence electrons. So this is why covalent bonds happen. Okay, 5 different atoms here in this compound were able to all fill their valence shells at the same time. Pretty cool. So this is pretty nasty though, what we have here. It's not very pretty to read. So the way we're going to write this is our final answer. And let me get this out of the way. Well, I messed that up. All right, forget about it. Let's rewrite it. Okay, instead of these circles of the electron bonding pairs, we draw a line to represent it. So there's one, There's one, there's one. This line represents a bond. Okay? We write that instead of the circle and the 2 electrons. Last step is you draw in all the electrons that are not involved in the bonding. So let's go ahead and draw those in. Okay? Each chlorine should still have 6 that are not participating in the bond. Carbon is sharing all of its electrons. So there we go. Here is the Lewis dot structure for carbon tetrachloride. We went through a lot of work there, but once you get used to it, you can do this pretty quickly. All right, let me do one more, and then we'll be done. All right, let's do water. H2O. Okay, 2 nonmetals. So we have O, we have H, and we got H. Hydrogen has 1 valence electron. Oxygen has 6. No point putting them where I'm putting, it's just what I chose. All right. Hydrogen is weird. It's one of those that it can fill its valence shell with 2 electrons rather than 8. So it's just going to form a bond. So that hydrogen is now stable. Same thing's going to happen over here. All right. And if you count, oxygen now has 1, 2, 3, 4, 5, 6, 7, 8. So oxygen is good. So are both hydrogens. We're done. So now you redraw your answer. Colors aren't important. I just think it looks cool. There's water, H2O. All right. So what I want you guys to do, I'm going to give you several examples. I want you to try them, pause it and try them, and then unpause it and check the answers. All right. First example. Let's do K2O. Okay. Then let's do magnesium hydroxide. Okay. I'm going to leave a lot of space. So go ahead and write these down. Let's do O2. Let's do iron 3 chloride. All right. More space. Let's do CH4 and calcium iodide. All right. So if you can do these 6, you should be totally good to go on Lewis dot structures. So go ahead and pause it and give them a shot. Okay, first one, K2O. So, don't want to use red yet. We got K, O, and K. This is ionic, metal and a nonmetal. So let's go ahead and draw in our valence electrons. Potassium's got 1. Oxygen, 1, 2, 3, 4, 5, 6. So what's going to happen here, these potassiums are going to give up their valence electrons to the oxygen. Now I realize on your notebook paper, you can't quite move these dots around, and if you can, that's really cool. So if you just want to do like this to symbolize it, this is fine, because you're going to rewrite it anyway. You can do it however you want. Okay, so that's all we got. We're good there. So you write your answer. K plus, and there's 2 of them, and O 2 minus. There you go. All right, next one, magnesium hydroxide. This is another ionic bond here. So I'm going to go ahead and cut to the chase here, save some time. Magnesium hydroxide, we know it's ionic, so we know that it's going to end up looking like this. right? So let's do the crisscross method, which we should be pretty good at by now. Magnesium is in group 2, it's got a 2 plus. Hydroxide is a polyatomic ion with a -1 charge. We're going to crisscross, and MgOH2 is what we're going to get. And write in the charges. So there we go, magnesium hydroxide. Okay, next one, O2. This is covalent because oxygen is a nonmetal. So we'll draw in oxygen and oxygen. Okay, let's put in our valence electrons. Okay, let's move these. All right, so oxygen, having 6 valence electrons, needs 2 more. So what it's going to do is share 2. So let's do 1 bond there, and another bond there. So now, this oxygen on the left has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. It's happy. And we can assume the same thing on the right because it's the same molecule. So, oxygen that you have floating around in the air bonds like this. It bonds in what we call a double bond. Okay? So here's your answer. Oxygen forms a double bond. Alright, iron 3 chloride. We got Fe, we got Cl. Okay, same thing here. It's ionic, so we can go ahead and cut to the chase, use the crisscross method. Alright, because Lewis dot structures are generally meant for covalent compounds. So, iron has a 3 plus charge, chlorine has a -1. So, we crisscross, and there we go. That's all you gotta do. Okay, CH4. C, H, 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 H. Draw in our valence electrons. Okay, you're going to see carbon in a lot of covalent compounds, and it generally does stuff like this. It likes to share all of its electrons to get 8, and all the hydrogens each have 2. So to draw this as your answer, this is all you need to do. Okay, this is actually methane right there. Last one, calcium iodide. This is ionic. We have Ca and we have I. Stick those brackets in there. Okay, calcium is a 2 plus, iodine is a 1 minus. Crisscross, there we go. Alright, if you're having trouble with any of these, if you don't understand, please come see me after school. I'll try to be there every day. If you can't come after school, talk to me about it and we'll set up a time to meet. Maybe in the morning, maybe during CAT. We'll figure it out. Alright guys, that's it.